Good morning and welcome everybody to Calculus. So we're going to get started here with a little bit of a review on limits because I know how much you all love them. So here we go. So for the first 6 here, we're going to look at this graph to answer our limit questions. To remind you, the limit is an approximation. So we're just going to find the approximate value. Sometimes we get the approximate value, sometimes we get the exact value. So let's look at 10. 10 right here, it actually equals exactly that value because there's no hole, no break, no jump, and nothing like that. So this value is going to equal 0. This one says 6 from the left. So let's look at 6, and let's look at the left. So what's it approximately coming in from the left? Very good, it's 2. Let's look at -8. So it's the approximation of -8. So it's over here. So this is the exact value. So approximate value is actually where the hole is located because we're just finding out what it is just to the left and to the right. So this answer is going to be very good, -6. You're on top of it today. Next one for number 4 is -2 from the right. So I'm looking at -2 from the right-hand side. So I'm looking at this little chunk right here, and it's going up and up and up. It's going up and up and up forever. So what does that mean? Yeah, it's going to be infinity. Now let's look at, as we go out to infinity, of this function. So here we go. So here's the function going out to infinity, and if it keeps going and going and going, it's going to keep going down until, yes, you said it, -infinity. And let's look at the limit at 6. So there's a jump here, okay? So the left side and the right side are different values. Since they are different values, they are not equal, so this does not exist. So moving on here to number 7, given this, answer each of the following limits. So we're going to go 2 to the left. So we need to pick a value that's to the left of 2. So it's going to be this top one right here. This is left, because these are numbers that are less than 2, and this is right. So all you do is you just plug in that value into the left one, and that'll give you your answer. So this is going to be equal to 3 times 2 squared minus 1, which is, very good, 11. Do the same thing here. Try this one on your own. Did you get 13? Awesome. Oh, okay, you want me to show it? Sure thing. It's going to be 5 times 2 plus 3, which is 13. Again, I'm using this one for the right one. Now, do these match up? The right and the left have to match up. They do not. So what can I say? Well, that limit does not exist. Same thing here. So go ahead and try this one on your own. You got to figure out the left side and the right side and see if they match. So go ahead and try it on your own. You finished? Okay, so what happens when you plug a 0 into the left? This is going to give you a 4. Plugging a 0 to the right, this gives you a 4, so they match up. So this equals 4. Very good. And let's keep reviewing. So for limits right here, we're just going to just plug it in and see how it works out. So let's go for it. So plug in a 3, you're going to get 2 times 3 squared, which is 18, minus 5, which is 13. All right, very good. Neelish, stop talking. Pay attention, Neelish. All right, moving on. Plug in a 4. You're going to get 2 times 4, which is 8 minus 5, which is 3, all underneath the radical. Number 11, plug in a 2, and you're going to get... Uh-oh. What happens when you plug in a 2? Get 0 and 0. That's not good. You can't have 0 over 0, so you have to do some magic. Do you remember what we did? Yeah, very good. All we did was we factored. So this bottom one factors to x plus 2, x minus 2, and then these cancel. So you're left with the limit, as x approaches 2, of 1 over x plus 2. And now you're ready just to plug in directly. So plug in a 2, and you're going to get 1/4. Go ahead and try 12 on your own. You finished yet? Alright, well, I'll just kind of trail behind you a little bit here. Plugging in -3, getting you 8 zeros, so you have to factor these. So x plus 3, x minus 4 is going to be x plus 3, 2x minus 1, and these x plus 3's cancel out, so do the limit as x approaches -3 of x minus 4 all over 2x minus 1, -7 all over -7, which is 1. Good job, class. What about this one right here? What happens when you plug in a 0? You're going to get 4 over 0. So that means you have 3 options. You're going to either have infinity, you're going to have negative infinity, or you're going to have does not exist. So what you need to do here is you need to find numbers that are close to 0 on the right and the left and see if they match. So I'm going to pick positive 0.1 and negative 0.1. If I plug in a positive 0.1, I'm going to get 4 over 0.1 squared, which is positive. That's all I care about, if it's positive or negative. Plug in a 4 over a negative 0.1 squared, and I'm going to get a positive. The signs match, so my answer is going to be positive infinity. If the signs were each negative, it would be negative infinity. If the signs did not match, it would have been does not exist. Okay? 14 is too similar to 11, so we're just going to go ahead and skip it. Here we go, 15. This is a problem that a lot of you would just go ahead and say, oh, bubble button, but it doesn't always work. So this example right here, we are increasing faster on the bottom. So if you remember how we do this, we're going to multiply by 1 over x, every single term by 1 over x. So I'm going to get 3 minus 1 over x all over, or sorry, it should be 1 over x. It's your highest term. Your highest power is 2. So my bad. So over x squared. So I'm going to get 3 over x, 1 over x squared, and get 2 plus 1 over x squared. Limit as we go out to infinity. Now plugging in infinity. So if you have infinity on the bottom, it turns into a 0. So this is going to give me a 0 minus 0 over 2 plus 0, which is 0 over 2, which is 0. So use that same exact idea to go ahead and do 16. So the highest power is x squared, so you're going to divide every single term by x squared. Try that now. Do you get 3/2? Perfect. Same idea for this one. So you're going to multiply everything by 1 over x cubed, or just divide everything by x cubed, however you want to say it. If you do that, you're going to get 3 minus 1 over x cubed all over 2 over x plus 1 over x cubed. This is the limit. So this is going to give us this problem again where we're going to have this number over a 0. So we're going to have like 3 over 0. So we have 3 options. Since this is going to turn out to be an odd function and it's positive, odd positive functions look like that, and we're going out to positive infinity. So this answer is going to be infinity. Cosine, out to infinity. Cosine, by the way, repeats itself. So it's 5 cosine looks like this, over and over again. Is anything going to happen as we get out to infinity? No. So this one is going to be does not exist, because it is oscillating. Alright, now why was this so important? Because I'm going to tell you right now, there's a shortcut to do all of this. Isn't that so exciting? Because you all like limits so much. If you ever get a 0 over 0, like we did in this example right here, you can factor it, you can do other weird things to it if you want, or here's a shortcut. Take the derivative of the top, take the derivative of the bottom, and then take the limit. Okay? So let's go back to that example we just did. We know this is 0 over 0. So now we can apply this rule. This is L'Hopital's rule. I call it L-hop for fun. So we're going to L-hop it. So let's do it. What's the derivative on the top? What's the derivative of x minus 2? Very good, class. Derivative of x minus 2 is 1. All over, what's the derivative of x squared minus 4? It's 2x. So plug in a 2 now. What do you get? 1/4. Does that match my answer from before? It does. Amazing. And we did this example too. Oh my gosh. When you plug it in, you're going to get 0 over 0. So you got to L-hop it. So we do the limit as x approaches -3. So we're going to get 2x minus 1 all over 4x plus 5. Now, if you plug in again and you get another 0 over 0, you just keep L-hopping it until you can't L-hop it anymore. But in this case, this does work out to be -7 over -7, which is 1. That is great. Here's this example right here. So technically, if you were to plug this in, you'd get infinity over infinity, which is also an indeterminate form. So this one, you can L-hop as well. So let's go ahead and do that, because you're going to get infinity over infinity. So you L-hop it by taking the derivative of the top and the bottom. You're going to get 3 over 4x. Well, that's going to keep going to 0, because we have a larger power on bottom. So this is going to be equal to 0. You still need to know that rule. If you have an x on the bottom and it's the highest power, it's still going to go to 0. Let's look at 22. This one also goes to infinity and infinity. So you have to L-hop it. So you're going to get the limit. So x approaches infinity, and then you're going to get 6x over 4x, which this also still goes from infinity to infinity. So you have to L-hop it again. So you're going to get the limit. So x approaches infinity of derivative of 6x is 6 all over 4, which reduces down to 3/2, which is the answer that we got before. (23). Same thing. We're going to get all these infinities. Okay? So you're going to L-hop it. So you're going to get the limit as x approaches infinity of 9x squared over 4x. you still get your infinity and infinity. So you got to L hop it again. Take the derivative on top. You're going to get 18x over 4. When you plug in an infinity, you're just going to get infinity over a number. So the answer is going to be infinity. Try 24 on your own. Can I help you? I'm not here.
Would you guys like copy of the afterwards for the push for you?
No, you can check it.
Alright.
No problem. Alright. Alright, so we did this one right here. I'll do a different color. It's a little easier for you to see then. You plug in a 2, you're going to get 0 and 0. See how that L hop it? Just means take the derivative on the top, which is going to be 3x squared all over the derivative of the bottom is just 1. And then you can plug in a 2 now and you're going to get 12. So these limit problems have just become a lot easier. Again, this is not the quotient rule. That's a common mistake here. It's when you take a derivative of a ratio. So you're going to take the derivative of just the top, derivative of just the bottom. Okay? One more problem that's kind of a little strange, but let's go ahead and figure it out together. So we have a function f, which is 3x plus 2e to negative 3x minus 2, and let g be differentiable function such that we know that the derivative is 4 plus x. Also known that the limit of g is equal to 0. Find this limit right here. So let's do a direct plug-in. So when I directly plug in a 0 into f, I'm going to get 0 plus 2 minus 2, which is 0. And I just know this information as well, so that gives me a 0. So I'm kind of stuck. So I have to take the derivative. So I'm going to do limit as x approaches 0, derivative of the top, derivative of the bottom, which is the limit as x approaches 0. What's the derivative of the top? Well, what's this derivative? It's going to be 3. Chain rule, minus 6, e to the negative 3x. Derivative of negative 2 is just 0. And this tells me the derivative is 4 plus x. Can I plug in a 0 now? Yeah, I totally can, because this is going to give me, when I plug in a 0, 3 minus 6 all over 4 plus 0, which is negative 3/4. So there you go. I hope you enjoyed the lesson, and good luck on your homework.